Hello and welcome to this complimentary webinar. Today we have a title of Looking Beyond the Central Composite Designs for RSM DOE. As you know, we have a software solution tool called MODE, which is part of the Geometric suite of data analytics tools. And today we're discussing some of the perhaps less known DOE designs for optimization or RSM as it is also called. Here we have a little overview of today's presentation. First of all, a little introduction to RSM as an objective and also the designs that are available. We will go over the design wizard in the MODE software and see how it will help the user to select an appropriate experimental protocol for optimization. And the RSM designs that we will be covering are central composite designs, the Threelevel full factorial designs, Schaffner designs, Boxbank designs, and Dalek designs. Towards the end of this presentation there is a demo, and the final part consists of some concluding remarks and also a little Q&A session. So should you have any questions, just use the question tool and we will then address all the questions at the end of the presentation. So as an introduction to this presentation, we can say that when we are entering into the optimization objective in the MODE software, usually MODE will recommend the design coming out of the central composite design family. And inside that family we have three implementations. We have the CCF, the CCO, and the CCC design alternatives, and I will come back to their naming and their geometrical properties. Now, one reason why this type of design family is often favored is because if you are starting out a DOE with screening design, using a full factorial design or a fractional factorial design, and you want to continue, you can with very small measures go on with results from the initial factorial or fractional factorial designs and convert those designs into either the CCF, CCO, or CCC designs. In addition to these designs that are covered in great detail in our training material and also, let's say, introductory level webinars, we will today discuss the Threelevel full factorials, the Schaffner, the Boxbank, and the Dalek designs. At the heart of the design generation procedure inside the MODE software, we have this design wizard, where after you have defined the factors and responses and indicating which experimental objective you would like to perform, you have an overview of all designs that are defined for a certain situation or a certain problem complexity. And the design wizard that we see in the screen right now relate to a problem where you have 5 factors and all factors are continuous and have no complicated facts associated with them. And we will also come back to this select model and design page when we do the software demonstration. We start now with the central composite designs, CC central composite designs. They have 3 alternatives: face-centered, orthogonal, the O is for orthogonal, and the C is for circumscribed. And we can see here in the bottom part of this slide how they relate to one another. In the central composite face-centered design, you have the factorial part, the black points, and the replicated center points, the red dots, and you are then adding the axis points or the star points, which are green on this slide, and you are placing them on the center of the faces or the sides of the cube. So with CCF, you will maintain the low and high factor levels that you set in the initial screening stage. The other, you can say CCF is one extreme. The other extreme is the CCC, which differ from the CCF in regards to how the green points are positioned. Now the green points are positioned outside the cube. The green points are circumscribing the cube, and put very simply, you can say that the corners of the cube and the green points lie on the surface of a sphere or of a football, or approximate that at least. And in between the CCF and the CCO design, CCF and CCC designs, you have the CCO design. So in the CCO design, the green points are in between being positioned on the center of the faces and the position where you have them when you do the CCC. The CCC spans the largest volume, and it also means that it has 5 levels for each factor. Also the CCO has 5 levels for each factor, but the CCC spans a slightly larger volume than the CCO. The CCO will have orthogonal square terms, and we will come back to that fact when we compare some of the other designs towards the end of the presentation. And that comparison is done regarding or using correlation matrices. Another possible design solution for RSM is the 3-level full factorials. They are simple extensions of the 2-level full factorials. And here we see to the left the simplest member in that design family with the code or the notation 3 raised to the power of 2, 2 factors in 3 settings, and that becomes 9 combinations. And to the right of the slide we have the 3 raised to the power of 3 analog in 27 runs. For those of you who have a sharp eye, you will note that the CCF in 2 factors and the 3 raised to the power of 2, they are equivalent designs. The next design member in this family is the 3 raised to the power of 4 in 81 runs, and MODE also supports the 3 raised to the power of 5 in 243 runs, but above those we don't have them implemented. And I think you can understand the sort of characteristic property of, or characteristic hallmark of these designs, and that is the very rapidly increasing number of experimental runs that are encoded. So for practical purposes, it is the 3 raised to the power of 2 and 3 raised to the power of 3 analogs that are most frequently used. Another family of designs is the Recht-Schaffner family. Last week we gave a webinar on the 2-level designs arising from this family that are used in screening, and I will refer to that recorded webinar for the details on the 2-level Recht-Schaffners. In this webinar we are discussing 3-level designs which are used in optimization, and the Recht-Schaffner designs are really interesting when you have 6 or more factors in the RSM, because they require much fewer runs than the classical CCC, CCF or CCO designs. But of course there will be a price, and the price you will see is rather large correlations among some of the higher order terms in the models. These designs are very compact in the sense that they will have as many experimental runs in the DOE as you have terms in the model, so you have a sort of a saturation, and the saturation property I was also discussing in the webinar last week. So the aim of these designs is that you will have to estimate an initial model and try to optimize the model by dropping the non-significant terms and thereby recover or gain some degrees of freedom. You will need some degrees of freedom to stabilize the residual analysis and other diagnostic tools. On this slide we see first of all I should say that the number of runs required for the 3-level Recht-Schaffner designs is this expression here. And it's also then recommended to add at least 3 replicated points, preferably at the design center to that number. And in the lower part of this slide we see geometrically and in terms of a worksheet the experiments that are included in the 3-factor analog, the Recht-Schaffner design in 3 factors. And we can see that what has happened is that you can say we start from the full CCF in 3 factors, and we start, or this design means you start to drop some corners and some centers of the sides until you are down to the number of runs that is equal to the number of terms in the regression model. So there will be a mix of runs that are dropped, some corners, and some centers of sides. Another design family included in the model software for optimization or RSN is the Boxbank design. They also have 3 levels per factor, and for some number of factors they are really economical. What you can see here from the illustration is that the characteristic property of these designs is that you will do the experiments not in the corners but at the midpoint of the edges. So the Boxbank designs are then of interest if experiments in the corners are undesirable or impossible, and particularly you would here think of perhaps the what we call the minus 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 corner and the plus 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 corner. The Boxbank designs are very good designs and they support quadratic models, but they are difficult to arrive at if you have started out with the full factorials, because with the full factorials you would have the corners, so to say. Another design family inside the model software for optimization is the Dalek design. And the Dalek designs have some really interesting properties. They are easy to build upon and you can extend them to upgraded designs, and this property I will come back to in 2 slides. They support quadratic models. You have all main effects, all 2-factor interactions, and all quadratic effects without any risk for confounding. From a geometrical point of view, the Dalek designs are polyhedrons based on hypertriangles or simplexes, and in the simplest case it will be a hexagonal structure. And one property exhibited by the Dalek designs that are lacking for many other of the design families implemented in the model software is that they actually have uniform space filling properties with an equally spread or equally spaced distribution of points that are lying on so-called concentric spherical shells. The Dalek design in 2 and 3 factors are seen on these 2 illustrations using plots from the model software, and you can see the benzene ring-like structure, if you wish, for the 2-factor analog. What people are usually not aware of is that in a Dalek design the number of levels is not the same for all variables. So depending on how you are entering or defining the factors, and now we're talking about the 2-level factors or continuous factors that you define with a low and high setting in the usual way in model, is that you will have different number of runs depending on which factor is entered first and in the middle and towards the end. And here you see the number of levels for each factor for the situation involving 2, 3, 4, 5, and 6 factors. And the level 5 here, that is for the factor that you define first. And you can see, for instance, that if you have 4 factors in your RSM problem, the first factor, if you select a Dalek design, will be exploited or tested using 4 settings, 7 settings for the second factor, 7 settings for the third factor, and only 3 settings for the last factor. So if there is some factor that is difficult to change, or you're reluctant to change it, or you think you know its influence very well, maybe that should be the last one in the DOE for the DOE problem of the Dalek design type. The number of runs encoded or required by a Dalek design is this here, and the +3 is what we say to have enough replicates. I was mentioning this buildability property, and here we have tried to exemplify that. You see the orange and let's say yellow benzene-like structure or hexagonal structure, and you can see how you can upgrade or form a second generation Dalek design in terms of these 3 experiments and how you can then reuse some of the original points or previous points. We now come over to a design comparison section, and we will work with 5 factors, and all the designs support quadratic models. So you will see 5 linear terms, 5 quadratic terms, and 10 two-factor interactions, a total of 20 columns in the correlation matrix. The CCF, which is the default in MODE, because we are arguing that if you're arriving from a screening design of the factorial type, then it's easier to modify it or upgrade it to become a CCF where you maintain the low and high settings. But technically you can easily change to any other design. If you have the CCF, you will see that you have significant correlations among the quadratic terms in the model, and the coloring threshold in MODE is 0.3. So as soon as you go above a correlation between any pair of terms exceeding 0.3, you will have a coloring of that particular cell in the correlation matrix. The CCO, which is in between CCF and CCC, has 0 correlations among the quadratic terms, and that's what I said. That's why it's called orthogonal. So you have here slightly larger volume of the design, but the design is not rotatable. The CCC design is rotatable, and here you have the largest correlations among the quadratic terms of around minus 0.14 or so, which is still relatively small. We move over to the Boxbank design. It has also correlations of similar magnitude to the CCC design. So this is also a very good design. We come to the Dalek design. We get more, let's say, off diagonal values that are non-zero, and that is arising because we have this different number of settings for different factors. For 5 factors, we can go back. For 5 factors, we have this situation, 5, 7, 7, 7, 3, and that will have an influence also on the appearance of the correlation matrix. Overall, the largest or most complicated correlation pattern arises for the rest Schaffner designs, and that is because you have on purpose dropped corners and sometimes also centers of sides in order to limit the number of experiments if experiments are expensive, and you try to recover degrees of freedom by dropping non-significant model terms. So the price you're paying with the Schaffner design is increasing correlations. We will now go over to the demonstration part and look into this, and then we come back to the PowerPoint presentation for a few rounding off comments. So I will start with just overviewing inside the MODE software what it looks like when using the design wizard in what we call the experimental mode. Inside MODE, you can very quickly define a number of factors. And this is also a principle I was using the previous webinar last week, just to very quickly try to get an overview and feeling for how costly you can say a certain problem will be in terms of how many experiments are required. So I'm just typing x1, x2 up to x5 and pressing the return or enter button on the keyboard. And then you have factors that are pre-configured to run from -1 to +1 just to be able to exploit a certain complexity. And we just define some response. It's not really critical for just exploiting the different possibilities. And we now use the optimization entry here. And then we see this select model and design page, which is the one I was starting out with in this presentation. You can see that when you're doing RSM DOE, all models are of the quadratic type, and they differ in terms of the number of runs required. For every design that you highlight, you will have a little explanatory note in the lower part of this page that is called Select Model and Design, just giving the most essential properties of a certain design. And regarding the CCO, the CCF, and the CCC, they only differ in regards to how the axis points or the star points are positioned. There is no difference with regards to the number of runs required. We have here also then the full factorial design, we have the Boxbank design, we have the Dalek design and the rest Schaffner design. You also have a de-optimal entry if there is a certain non-standard demand that you have. That the optimal designs we have covered in other recorded webinars last year, and they are found on our website. The de-optimal designs are also of relevance if you, let's say, have a specific model of a specific configuration. Maybe you know you have a specific, let's say, a cubic model term in mind, but you don't want all the cubic terms that are theoretically possible. It's only one cubic model term you're after. These and other types of requirements. Then, regardless of which design you are selecting, you are clicking Finish. After clicking Finish, you will get the worksheet. And when you have a worksheet, you can go to the worksheet tab and use a tool called the correlation matrix, which I hope will come up here. There it is. And that is basically what I have been doing when doing these screenshots for the different experimental plans. I will go back and just show you if you now want to modify a certain design. You go to the Home tab, you can just again restart the design wizard and say you select a Dalek design, for instance, and instead of the, I think we have the Boxbank up, you just experiment with the Boxbank and you have a number of different levels. And if you want to see which experiments are going to be part of this DOE, in addition to exploiting properties using the correlation matrix, you can also visualize things using the scatter plot tool. Here we can make a plot of, let's say, factor 4 and 5, where you will have 5 and 3 levels, if you remember the table. Here you see that factor 4 in this Dalek design has 7 levels, and the last one has 3 levels. There are different things you can do and just exploit the properties of the design before you even launch it, so you know if you have a good or a bad or let's say a promising design at least. The illustration of the case dataset in this case is the DOE exercise that is called Pyrrole in our exercises compilation. It deals with the application of DOE in organic synthesis. It is one of the many applications contributed by Professor Torbjörn Lundstedt and his co-workers. And in this particular application, they were synthesizing an internal standard to be used for gas chromatography. And they were, in this particular study, optimizing the yield of an intermediate compound leading forward to the final internal standard. And they have been doing screening experiments, and now when we enter the story, we are in the optimization. And there are 2 factors. It is the amount of pyrrole, which is the starting compound, and the amount of a potassium-based catalyst. So we have some settings, and then it is the yield of the intermediate following 30 minutes of experimental duration, you can say. We see the protocol here. We can minimize the things, and here we see the experimental plan. You can use a scatter plot just to visualize the geometry. This is just 2 factors, so it's very straightforward, and you will see the benzene ring-like or hexagonal type distribution of the points. We can use either the analysis wizard to analyze the data or proceed with all the buttons in the diagnostics and interpretation group under the Home tab. You will see that the quadratic model is a very, very strong model. We have good performance statistics, and we also have two very prominent quadratic terms for each of the two factors, which means that when you make, for instance, a response surface plot, you will have a very prominent peak of the mountain where you have optimal yield. And if you go back to the worksheet and just look at the experimental values, the highest reported yield was around 24-25% in the literature before Torbjörn Lundstedt started to undertake his experiments. And you can see that in the top of the estimated response surface, the yield is estimated to 68% or so, which is substantially above the reported yield in the literature. So this was a little demonstration about one of the, let's say, less frequently used design families for optimization, the Pyrrole example based on a Dalek design. I will now go back to the PowerPoint part for a final little discussion, and you see a very busy table in the lower part of the slide, and this table is an overview of, let me turn on again the pointer. This table is an overview running from 2 factors up to 10 factors. It is comparing the central composite design family, the Threelevel full factorial design, the Schaffner design, the Boxbank design, and the Dalek design. And for each number of factor, you have the number of runs encoded, and this number of runs includes 3 center points. You have the condition number of the design, and you have the correlation coefficient, the largest correlation coefficient of any pairwise correlation in the correlation matrix. And for all design families except the Dalek design family, the largest correlations are found between the quadratic terms. For the Dalek design family, the largest correlations occur between different 2-factor interactions that are then sort of mixed up. And in general, you can see that the more factors you have, the larger the condition number becomes, and that is of course expected. In this table, NA means not available, and NI means it is not implemented in the model software. And you can see that, for instance, if you have a rather large number of factors, 6 or 7, the Schaffner designs are interesting alternatives to the central composite designs. There are also possibilities with the de-optimal designs that you should not forget to exploit. One design that is particularly interesting when you have 3 factors is, in addition to the Schaffner design, is the Boxbank design. The Boxbank design in 3 factors has relatively small number of runs, for instance, and there are also other specific cases. Another one, if you are not going for the Schaffner design because it has high correlations, you can also go for the Boxbank or the Dalek design when you have 7 factors. Usually we say that the recommended number of factors in an RSM DOE is 5. If you have more than 5 factors, 6, 7 factors in a problem of an optimization type, then the number of experiments will sometimes be prohibitively large, and we would then suggest you run a second stage screening to really sort out the most critical factors. And I think that is what I wanted to say. The final thing to mention is that we are continuing our stroll throughout all the properties of the geometric suite of data analytics solutions. We have a series of webinars going on every Friday, and we have past MODE and Easy Analytics, and we are on our way leaving SIMCA going towards SIMCA Online, and the next webinar is on Friday, April 21, and you're most warmly welcome to sign up and join that presentation. I think this is the thing I wanted to say. I see there are a couple of questions in the question tool, so I will just stop the recording and very shortly be back and try to respond to these questions. So thank you very much for your time and attention.